Hello everyone. It's been over a year since I posted the video about automating my HVAC duct booster with a relay controlled by the furnace's electronic air cleaner control signal. That video got quite a bit of interest and some good comments. Some of the commenters' ideas have been helpful and constructive, and I made some upgrades as a result. I also noticed a video on another channel where a duct booster motor is directly driven off the electronic air cleaner signal on the furnace control board. I definitely don't recommend doing it that way, and I'd like to explain why. So, it's about time for this update video. As far as directly wiring a motor to the EAC signal, there are good reasons why I wouldn't do that. I don't think it's a good idea in general to put a motor load on an electronic output that's designed to be used as a control signal. I've looked at a few furnace control board schematics, and the ones I've seen use an onboard miniature relay component to control the EAC signal output. I'm thinking that signal is designed to enable a relay within an electronic air cleaner or a light or some other low current device, and that it certainly isn't designed to drive a motor, which might even possibly void a warranty. I don't know. The EAC output is limited to 1 amp at 120 volts. The relay coil I use draws 31 milliamps. That's 0.031 of an amp. So it barely registers. There's no risk of overloading that output and damaging the expensive control board by using this relay. However, I'm actually updating it with a fuse to protect it from the highly unlikely event of a downstream short circuit. Motor power circuits are usually designed to deal with the special problems of motors. For one thing, when a motor starts up, it draws anywhere from 3 to 5 to even 10 times its normal operating amperage for 0.2 of a second or even more. Then when it shuts off, there's a bigger challenge for the relay contacts. Trying to open up under spring pressure, the contacts draw an arc between them until they're far enough apart to stop the current from jumping across. This causes pitting of the contacts over time until they're too burned out to work without heating up. Mind you, that excess heat would be generated on the control board. Motor bearings also wear over time, causing greater current draw and more heat. Motor contactor relays are designed to handle these problems. You'll see a horsepower rating on them. The relay I used is rated to switch 10 amps in general, and more importantly, it's rated for a 0.5 horsepower motor. So it's a better choice to prevent possibly burning out the furnace control board, which could be catastrophic in midwinter. Is the furnace EAC signal rated for horsepower? Highly doubtful. There's also the possibility of a short in the motor or motor wiring that could easily kill the furnace control board. And if you think about it, the components are soldered onto the control board and powered through solder traces on the board. What happens when solder gets too hot? I like to sleep at night, so I do things with an abundance of caution. Let's calculate the expected motor current using the familiar Ohm's Law wheel. The HVAC duct booster is rated at 37 watts. So, referring to the power quadrant of the wheel, we can say watts equals volts times amps, which means amps equals watts divided by volts, and the current quadrant of the wheel agrees. The motor's 37 watt rating divided by 120 volts equals 0.308 amps. So I can base my fuse size on 0.308 amps, right? Wrong. Why did I say that's wrong? Did you catch my intentional mistake? Let's take some current measurements on the running duct booster and we'll learn why that's wrong. So I'm doing my duct booster electrical measurements using a kilowatt meter. The power source for these measurements is just a cellar wall receptacle. Voltage is 120 volts AC. And frequency is 59.9 Hertz. I actually took readings at 25%, 50%, 75%, and 100% speeds. But I don't need all those numbers to accomplish my goal here. So I'll show the first measurement, then jump to the high speed measurement, which is all I really need. The duct boost controller is currently set at its lowest speed down by the L. And the current draw on low speed is 0.36 amps, also known as 360 milliamps. I'm most interested in motor current for selecting an appropriate overcurrent protective device, but the low speed power consumption is 18 watts. And then the low speed volt amps is 43 VA. The power factor at low speed is 0.42. So if you notice, if you take the 0.42 and multiply it times 44 volt amps, it's teetering 43, 44. Multiply it times 44 volt amps, and that comes up very close to 18 watts. It's actually around 18.5 watts. It's good to be aware of power factor when you're working with inductive loads like motors, because basically reactive loads like motors are why we use volt amps and not watts when we're calculating our AC current loads. I'll show you an example later in this process. Okay, so now I set the duct booster to 100% speed. That's the high mark. As far as it goes, that's high speed. The current draw is 0.56 amps. It's using 37 watts of power at 67 volt amps. And the power factor is 0.54. These are all the readings I took, but I really only need the high-speed current for sizing the motor circuit fuse. So I'm using 0.56 amps. Why is that so different from my first calculation of 0.308 amps? Let's explore the topic of power factor a little bit. This should give us enough information to understand what's going on. These are drawing representations of our AC voltage and amperage sine waves. Notice they appear to be in phase with each other. It appears more obvious they're in phase when we superimpose them on the same axis. And if we multiply our measured volts times amps, we get 67 watts. So why is the duct booster rated at 37 watts? It's because inductive loads like motors and relay coils cause a phase shift in the current waveform. Current lags voltage, as seen here. There's a delay in the current. So the apparent power is 67 volt amps, and the real power, which is watts, can be found where the two sine waves intersect. Remember we read a power factor of 0.54? Power factor times volt amps equals watts. Watts are the actual real power being used. The difference between apparent power and real power is basically just some wasted energy. because it doesn't do work. The less power factor you have, the better. It's more efficient. But the important lesson here is that we always use volt amps when we're calculating loads for our AC circuits, because watts aren't always a good indicator of the current in the circuit. And the product specs I was using at first didn't provide the information I need, which is amperage. So the only good way to size this fuse is to measure the motor's actual high-speed current. Alright, let's talk about fuse holders and fuses. I chose this fuse holder based on several factors, including fuse size and type, voltage and current ratings, and cost and availability. The brand is NTE Electronics, and the part number shows here. This is a good beefy fuse holder. It's overkill for what I'm doing with it. I could have bought its smaller twin, but these were cheaper. We can see it's rated for 20 amps at 250 volts, and that it bears the UL recognized component mark. The recognized component mark is a type of quality mark issued by Underwriters Laboratories. It's put on components that are intended to be part of a UL listed product, but which cannot bear the full UL logo themselves. I prefer at least using UL recognized components rather than one of the many cheaper unlisted knockoffs in circulation out there. It's had legitimate third-party testing and oversight, so I'm confident this will be a safe product. Now that I have the duct booster power details I need, I can select my fuses. Let's have a look at this helpful list of fuse selection criteria I found at instrumentationtools.com. In the interest of time, I'll fast forward to show my answers. The normal operating current is 0.56 amps at 120 volts AC. I actually measured the ambient temperature by the furnace control board and it was 68 degrees, but I'm going to say 77 degrees because it'll be warmer in the summer. What is the available short circuit current? It's 8,000 amps. 8,000 amps, what? I'll explain that momentarily. The maximum allowable temperature rise is not really critical in a cool air handler. Are there inrush currents available? Yes, it's a motor power circuit. Motors have inrush. Is the protective device being used for short circuit protection, overload protection, or both? I'm using it primarily for short circuit protection. What are the physical size limitations? Well, there's a small amount of space available in the cabinet, and I'm installing a small fuse, so it isn't a problem. Is the PC board surface mount or through hole? This isn't a PC board mounted fuse, so it's not applicable. Does the fuse need to be field replaceable? Yes. Is resettability an issue? No. What safety agency approvals are needed? I like UL or ETL. How will I mount the device? Well, this is an inline fuse holder. What are the cost considerations? I consider this to be low-cost insurance. So now, for those who don't know, why did I say the available short circuit current is 8,000 amps? If there's an actual voltage short circuit, which means the line conductor is directly connected to the grounded conductor, the transformer out on the utility pole can deliver 8,000 amps through the circuit until an overcurrent protective device, such as a fuse or circuit breaker, opens up and stops the current flow. If you look at a circuit breaker or fuse, you'll find an AIC rating. That's a current interrupting capacity. Most of your residential branch circuit breakers will be rated for 10,000 amps. That means the overcurrent protective device can instantaneously, in quotes, open up and interrupt the very high current flow of a dead short without the internal contacts being welded together due to the arc that's jumping across them as they open. Most residential main breakers will have an AIC of 22,000 amps. So here's some examples. This is a square D home line 15 amp circuit breaker. See where it indicates 10 kA? That's 10,000 amps. But we can also see the interrupting rating of 10,000 amps is molded right into the side of the case. Here's a 60 amp square D QO circuit breaker. It also indicates 10 kA right on its face, and its interrupting rating of 10,000 amps is molded right into the case. And here's one of the classic Bussmann fuses I'm using for my project. Even these small 1/4 inch by 1.25 inch glass fuses, AGC 1/4, are rated to interrupt 10,000 amps at 125 volts AC. One other commenter said he'd use a fuse to protect the electronic air cleaner output on the furnace control board. Now, that output is rated at 1 amp, and the relay coil is rated at 31 milliamps at 120 volts AC. 31 milliamps is 0.031 amps. So there's no risk of overloading this 1 amp EAC circuit with this relay. But the slim possibility of a short in the relay or circuit might justify using a fuse to protect that expensive furnace control board. So out of an abundance of caution, I added a 1/4 amp fast blow fuse to the EAC output signal. Why did I use a 250 milliamp fuse? Well, it's because I happen to have an abundance of them in stock. MDL1. So why spend $5 to $10 for a box of 100 milliamp fuses? AGC 1/4. A 1/4 amp fuse will certainly protect a 1 amp rated circuit. The fuse on the EAC signal needs to protect the circuit from a short circuit at 1 amp or less. For the motor circuit fuse, well, the HVAC duct booster comes with a 120 volt plug. So it's designed to trip either a 15 amp or 20 amp circuit breaker if there's a short, or just let the smoke out of the on-off switch / speed controller if there's a short. So my main goal is to protect the relay contacts from overcurrent. They're rated for 10 amps. Okay, if I'm following NEC section 430.52, rating or setting for individual motor circuits, and table 430.52, the circuit time delay fuse ampacity for a single phase motor can be no more than 175% of the motor's full load current. So my high-speed current of 0.56 amps times 175% is 0.98 amps. However, if that calculated value doesn't correspond with a standard fuse size, there's an exception that permits using the next higher standard size fuse. I was planning on using a 1 amp slow blow fuse anyway, so my Bussmann MDL1 fuse selection works out fine. And my relay contacts will be very well protected. One helpful commenter said the relay shouldn't be mounted on the bottom of the furnace cabinet. He pointed out that if the AC evaporator, which is on top of the furnace, should happen to ice up, water will drip down inside the furnace and pool up in the bottom, right where the relay is. So that could become a problem. And it actually turned out that the drain tube on the evaporator housing happened to clog up this summer. The evaporator housing has a drain point here that is plumbed into this tubing, which runs down into that condensate pump, and that pump takes it and pumps it up through this tube out over to the sump crock. In addition to that, there's a drain tube coming out of the humidifier that runs down and tees into this drain tube and down into the condensate pump. So the problem I had here was that just below this tee, the line got plugged. It was just plugged with a bunch of schmutz that built up in there, started up here and built up, and the water from both here and here stopped flowing. They both backed up. This line was actually full all the way up to the level of this drain. But inside the evaporator housing, since the water had no place to go, it started dripping down inside the furnace. The relay, or really any electrical items, shouldn't be mounted on the bottom of the cabinet here. And that's because if the evaporator ices up, water can drip down in and pool up inside here. So as it happened, that drain tubing on the evaporator plugged, and I had water dripping down inside here, and it was starting to pool up back there, but there's actually enough openings in the bottom there. There's like spaces between the sheet metal. It's actually not very impressive that there's big leaks in the bottom, but the water dripped out, and so it never accumulated enough to touch the relay. However, I'm going to relocate this relay in the event that something happens where there might be more water in the bottom. So that's a potential danger. You don't want this thing to get wet. I could just screw it up there. 2 holes, long screws, and that'll securely keep it high and dry. That's my goal here. Okay, well, I found a better place to mount this relay. Right up in there. It's underneath this cover and screwed to this plate, which is where this transformer is mounted. I didn't have to drill any holes. I think it makes for a neater installation. The hot wire here, which is now protected by a fuse, runs across here. It's this orange one going into the relay, and then coming out of the relay is the wire that goes out to the motor, and that's terminated up here to the motor cable. Down here, the EAC signal comes out here, protected by a fuse, and that goes up, and it's spliced to this wire, which is the hot side of the coil in the relay. And then the neutral side of the coil is just run down there and terminated where it was originally. So now there's nothing laying on the bottom of the furnace to get wet in case there's another event where something's dripping down. This is there's a good bit of clearance here, more than ½ inch. I put a 1 amp MDL fuse in here to protect the motor circuit, and I put an AGC 1/4 amp fuse in here to protect the EAC output. And that's that. It turned out to be quick and simple. And some of you may have been waiting for a look at my wiring diagram, so here it is. All that's left now is to test it. Another commenter pointed out that the power into the furnace should be controlled by the safety switch on the furnace access panel, which isn't a bad point. I mean, the risk here is minimal because the relay also automatically turns power off, but it's common sense to have all the power in the furnace switch off when the access panel is removed. So I rewired the relay to get its power through that furnace safety switch. The furnace access panel safety switch is rated for 16 amps at 125 volts AC. Notice it also has a motor horsepower rating. The furnace is powered by a 15 amp circuit breaker, so even the safety switch is protected from an overcurrent condition. And so it's okay to take the power for the duct booster through the safety switch, being that it's only 560 milliamps at most. Okay, this is the power conductor coming in from the branch circuit. So this is the power going into the switch. So the only tap on that power in here, it comes in from the Romex cable into this box and splices to the input on this switch. The output from this switch goes directly to this wire here that goes into the control module. So I'm going to cut it right in the middle, basically right in the middle. So I want all three of these conductors to be spliced together right here. I might have crimped that a bit too hard, but we'll put this cap on it, and these caps just screw on. You can feel that kind of lock on when it's all the way, when it's screwed all the way tight. And that's that. This fused power feed to the relay gets its power through the safety switch. So now whenever this panel is removed, everything in here is dead. That makes it just that much safer. And the power goes back on. Since it was installed a year and a half ago, the burning question may be, is this duct booster system still working? Well, I'm happy to tell you it's been working perfectly since day one with zero problems. Thank you for watching. Please take a moment to like and subscribe.